On to part two. Part two is also worth 13 points. Breakdown went something like this. 2 points for this one, 2 points for this one, 2 points for this one, 3 points for this one, 4 points for this one. All of these are finding some sort of a empirical formula, I believe. What's the empirical formula for a molecule containing? There's our percentages. They don't tell us how many grams, but if we just assume a 100-gram sample, then we can just replace any one of these percentages with grams. I'll have 18.7 grams of lithium, Li, 16.3 grams of carbon, 65 grams of oxygen. What I really need to know, though, is not how many grams, because we don't count by grams. We need to know how many moles. So all you have to do is divide it by its molar mass. Lithium, according to the chart, you divide by 6.94 grams per mole. And that's going to give you 2.69. Some of you rounded way too early and you ended up getting goofed up on some of your numbers. Carbon has a molar mass of 12 grams per mole. When you divide that, you'll get 1.35 moles. And oxygen, when you divide that by 16, you're going to get 4.06 moles of oxygen. These might not be readily apparent of which, how many times bigger they are, unless you're pretty good at doing math in your head. Suggestion, we need to know the ratio of moles of one to the other. Put the bigger one on top. We need these to be in whole numbers, so the bigger number on the top gives us the best chance. For instance, 4.06 moles of O divided by the smallest one, 1.35 moles of C, is going to be a relationship of 3 moles O to 1 mole C. So it's a 3-to-1 relationship. What about the lithium? I can do whichever one I want, but lithium's a bigger number, so I'm going to put lithium, 2.69 moles of lithium, on top of the smaller number, 1.35 moles of carbon. And that's going to be a 2 or 2-to-1 ratio. In other words, 2 moles of lithium to 1 mole of carbon. In other words, the simplest whole number ratio is 1 of these, 2 of these, 3 of these. LiCO. I'm writing them in the same order that they came up in the problem. Li2, 1C03. Lithium carbonate is Li2CO3. This next one, we have to figure out 2 formulas. One empirical, and one is the molecular, the one that's actually written. So the molecular, simply count it up. I generally will put the C's first and H because I know that that's how they're going to do it in the chemistry world. But if you did the H first, that's okay. How many C's do we have? 2. How many H's? 1, 2, 3, 4, 5, 6. 6. C2H6. But an empirical formula is the smallest whole number ratio. In other words, reduce this down. The empirical would simply be CH3, half as many as both of them. That's the simplest whole number ratio. This one just tries to relate it to some lab data. They're not going to just tell you exactly how much phosphorus, which is P, and chlorine, which is Cl, that they have. We have to figure it out. But ultimately, we're trying to figure out P, Cl. We're trying to figure out how many of those to how many of those, and it has to be whole number ratios. So we have to search a little bit for it, but not too hard. For instance, they tell us that there was 11.39 grams of P. And looking on my periodic table, phosphorus is 30.97 grams per mole. When I divide that out, it looks like I have 0.37 moles of P. For those of you who rounded real fast, you're not going to see the right ratios. Chlorine. Doesn't tell us how much, but they do let us know that if we started with 50.51 grams and 11.39 grams of it is phosphorus, whatever the difference is, and in this case the difference is 39.12, that's chlorine. So it's 39.12 grams of chlorine. How much does a mole of chlorine weigh? Check the chart, 35.45. So that's going to equal 1.1 moles of chlorine. Not readily jumping out at you of how much bigger this number is than this number, but the big number on the top, 1.1 mole of Cl was the big number. The smaller number on the bottom, 0.37 moles of P, and that equals 3 moles of chlorine to 1 mole of phosphorus. So PCl, we have to have 3 times as much. One mole of, I'm not going to write the 1, but if I did, it would be right there. Let me undo that. It's going to be PCl3, empirical formula. Next one. It's worth 3 points because not only do we have to figure out the empirical, but we also have to calculate the molecular. It's done with pretended it was in the lab, but when it gets right down to it, they tell us exactly how much carbon, 6 grams of carbon, exactly how much hydrogen, and exactly how much oxygen. Divide it by its molar mass, which you get from the periodic table, and you're going to get 0.5 moles of C to 0.5 moles of H to 0.125 moles of O. For those of you who rounded, you don't want to round too early in these because your ratios really will change. These ones seem easy. These ones seem like a 1-to-1 ratio. They're the same size, so however many C's we have, we must have just as many H's. How much oxygen do we have compared to them? Best way to get a whole number ratio is to divide the smaller number by the larger number, and in this case they're both the same, they're both 0.5, to get 4 to 1. It's a 4 moles of O to 1 mole of H. So I know it's got to be C something, H something, O something. But I have to have 4 times as many O's as C's and H's. So in 1 part C's and H's. So C, H, what am I doing here? 4 times as many, 0.125. Okay, so there I did. All right, backtracking. I put the wrong number on top. I said to put the big number on top, and there I put the smaller number on the top. It kind of works out. I could still go with it. Nope, I'm just going to erase it. We won't talk about getting the wrong one. Big number is 0.5 moles of C or H. They're the same. Smaller numbers, 0.125 moles of O. That's 4 moles of C and H to every 1 mole of O. So I had that backwards. It was just flip-flopped. If I would have labeled it correctly, it's still telling the same story, that it takes 4 to 4 to 1 ratio. But I really wouldn't write that 1 right there. That's an empirical formula. It's the simplest whole number ratio. If we did have a mole of that stuff, we'd have carbon. 12 grams of carbon times 4 is 48, plus 4 hydrogens is 4, plus an oxygen is 16. Add those together, it equals 68 grams per mole. But they said that the real molar mass is 136 grams per mole. How do those compare? 136 grams per mole compared to 68 grams per mole equals 2, twice as much. Really, we have to have twice as much of everything. So instead of having C4, well, our empirical formula is C4, H4, and 1 oxygen. But our molecular formula has to be the same ratio, but twice as much of everything. C8, H8, O2. And the last one, worth 4 points because it's got some, basically it's lab data mixed in, but it's just a empirical formula, very similar to what you guys did in the lab when we went and dissolved zinc with hydrochloric acid. Okay, so let me start reading through this. It's similar to the zinc chloride. I have hydrobromic acid, lead, hydrogen gas, so many things. What am I really, oh, here it is. It's going to make copper bromide, and what I'm trying to figure out is Cu, however many Cus there are, and however many Brs there are. So they label it X, Y, or question mark, question mark. So in other words, I have to figure out how much Cu, which is copper, how much bromine. Well, they tell us, nope, they don't tell us anything. They do tell us that if we have copper in a beaker, it weighs this much. But the beaker alone weighs that much. Subtracting, you'll get 15.36 grams of copper. Then we know that after the reaction was done, it gained a bunch of weight. And the only thing that it gained is going to be bromine or bromide. 248.51 minus 219.71 means that it gained 28.8 grams, and that had to have been the bromide. So the first thing is just analyzing lab data to figure out how much of each substance did we use. But that's not counting the atoms. We can't see those atoms to count, and it'd be a big number. So we need to figure out how many moles that is. Copper, you just simply divide by its molar mass, which you get off the periodic table, 63.55. That equals 0.24 moles of copper. Bromine, find bromine on the chart. It has a molar mass of 79.9 grams per mole. So when you divide that out, you're going to get 0.36 moles of Br. I look at those numbers and it's not very apparent how they compare. Is one of them twice as big, 3 times as big, 4 times as big? I'll do a mole ratio. Big number on top, 0.36, and that happens to be bromine or bromide. Little number on bottom, 0.24 moles of copper, and that's going to equal 1.5. That's not a whole number. What does that mean? 1.5 moles of Br to 1 mole of copper. So what I think I need to do is take that 1.5 and put it here. Take that 1 and put it over here, but we can't have partial atoms. We can't have partial, they have to be whole numbers. So this didn't end up as whole number ratio. So now I have to do something and figure out how can I change this and keep the same ratio, but end up with a whole number. Well, 1.5 is easily, if you simply multiply that by 2, you'll get 3. But you also have to multiply the bottom by 2 to get 2. It's 3 parts bromine to 2 parts, whoops, 1 times 2 should be 2. 2 parts copper. So this 2 goes here, this 3 goes here. My empirical formula is Cu2 Br3.